So functions of operator, that means that means a function which is made up of the operators. So we will study about these functions. Let capital F is the function of operator A, and if A is a linear operator, underline it, linear operator, then by Taylor's expansion, function f a can be expressed in the power series of in terms of power series of operator A, that is function f a can be expressed as summation n is equal to 0 to infinity an capital A operator to the power n. So this is equation number 1, where an is just an expansion coefficient. So let us understand these function operators by an example. Let function operator f a is e to the power a into operator a. So this e to the power small a capital A can be written in terms of Taylor expansion as n is equal to 0 to infinity a to the power n capital operator A to the power n by factorial n, which is nothing but the unity operator I plus a capital of A operator divided by factorial 1 plus a square capital A operator square by factorial 2 plus a cube capital A operator cube by factorial 3 and so on. Thus we see that functions of an operator can be expressed in terms of the Taylor's power series if the operator A is a linear operator. Next, we have learned about the commutators involving the operators. Now we will learn about the commutators involving the function operators, that is commutators of the function containing the operators. So if capital A commutes with another operator B, then operator B commutes with any operator function that depends on operator capital A, such that if A B commits, then it is equal to 0. That also implies that operator B commutes with function operator F capital A. So we should notice the order A, B. Here order is B, F, A. Now in particular, if A commutes with operator A itself and also with any other function that depends on operator A, that is, it may be G, it may be K, and so on. So that means in particular, this is not general case. In particular, if A commutes with any operator A, then it also commutes with any function that depends on the operator A. That is, commutator A if A is equal to 0, then operator A to the power n if A is also equal to 0, and commutator if A GA also 0. Now we learn about the Hermitian adjoint of function operators. So friends, in the previous lecture, we learnt about the Hermitian adjoint of operators. Now we will talk about the Hermitian adjoint of function operators. Function operators. If you are interested in the previous video lecture based on the operators, commutators, Hermitian and skew Hermitian operators and their uncertainty relation, so please visit the video by clicking the I button in the above right corner of this screen. I will provide the link also in the video. So please you can watch those video lectures. So we are talking about the Hermitian adjoint of the function operators. If A operator A is Hermitian, then if A is not necessarily a Hermitian, it may be Hermitian, it may not be Hermitian. So if f is the function of the operator A, then adjoint of this function operator is defined as this f star a dagger. So as A is the Hermitian, it can be written as f star A. So we'll check whether when A is Hermitian, the function operator will be Hermitian and will not be Hermitian. So let us take an example that function operator if A is equal to e to the power A. Therefore, adjoint of this function operator if A dagger is equal to e to the power A dagger. that is equal to e to the power a dagger, and since a is the Hermitian, so it can be written as e to the power a, that is fa. So in this case we see that adjoint of the function operator is again a Hermitian operator. Now let us check. Now let us take function operator is given as e to the power ia. So in this case, adjoint of this function operator is equal to adjoint of this e to the power ia, and that is written as minus e to the power minus I a dagger, that is equal to e to the power minus ia. So we see that it is not Hermitian in this case. So if A is Hermitian, an operator function which can be expanded as so, if A operator is Hermitian, an operator function which can be expanded as the Taylor's power series summation n is equal to 0 to infinity a to the power n will be Hermitian only if the expansion coefficient a is a real number. So, but in general, function operator fa is not Hermitian, even operator a is Hermitian. Right? F star a dagger is equal to summation n is equal to 0 to infinity a to the power n is equal to n is equal to 0 to infinity a star n star a dagger to the power n. So if so for the function to be Hermitian, this expansion coefficient should be real. Now relations involving function operators. There are 2-3 relations which we will prove in the coming video. For the information, let us see what those are. Commutator AB not equal to 0 implies that commutation of B with function operator A is also not equal to 0. If this is 0, then this will be 0. Otherwise, this will not be 0. In particular, e to the power A into e to the power B operators is not equal to e to the power A operator plus B operator. we can write e to the power a operator into e to the power b operator is equal to e to the power a operator plus b operator into e to the power commutation relation of operator a and b divided by 2. So this will be equal to this only when AB commutes. Now another relation e to the power A operator B e to the power minus A operator is equal to operator B plus commutator of AB plus 1 by factorial 2 commutator of A comma commutator of AB plus 1 by factorial 3 commutator of A comma commutator of A comma commutator of AB and so on. We can prove these two relations in the coming videos. So we can prove these two relations in the coming video. So please subscribe the Sai Academy channel so that you can know the upcoming videos on these two relations. Now we will talk about the inverse and unitary operator. Let's learn about the inverse and unitary operators. Friends, it is not necessary that there exists an inverse of any linear operator just just like as in the case of matrices. The inverse of a matrix exists only when its determinant is non-zero. Otherwise, it will not exist. So let us assume that inverse exists. So let us assume that an inverse operator exists, operator minus exists corresponding to a linear operator A. As defined by the relation operator A inverse operator A is equal to operator A inverse operator is equal to identity operator. So this is the unit operator or identity operator that leaves any state ket psi unchanged. So that means if we apply unitary operator on any ket psi, so it will remain ket psi. A linear operator, any linear operator, a linear operator U is said to be unitary if its inverse its inverse operator U minus 1 is equal to its adjoint. That means U dagger is equal to U inverse. So in this case, U will be said as a unitary operator, and then u dagger is equal to u dagger u is equal to identity operator. So in any linear operator, u is said to be unitary only when this relationship is valid. Also, the product of two unitary operator is unitary operators is also unitary. That means if there are two operators, that is unitary operators, then their product will also be a unitary operator. How? Let's see. Let u and v are two unitary operator. Then u v into uv dagger is equal to uv into v dagger u dagger, and this is equal to u v dagger u dagger, and this is equal to unity because they individually are unitary operator. Therefore, this is equal to u dagger is equal to identity operator. So the product of two unitary operator is also a unitary. Therefore, uv dagger is equal to uv inverse. And these results can be generalized to any number of operators. That means the product of any number of unity operator is also unitary. That means if A, B, C, D dash dash are the product of unitary operators, then they are also unitary. A, B, C dash dash dagger is equal to A, B, C, D into D dagger, C dagger, B dagger, A dagger, and that means equal to A, B, C, D, D dagger, C dagger, B dagger, A dagger, and so on. That is equal to A, B, C operator. This will be identity operator. So again C dagger, B dagger, A dagger, and this again will be unity. So therefore A operator, B operator to B dagger into A dagger. So again A operator into B dagger, therefore A dagger equal to identity operator. So that means the product of any number of unitary operator is also a unitary. That means A, B, C, D. That means A operator, B operator, C operator, D operator can be written dagger is equal to A, B, C, D operator minus 1. So far, we have studied the properties of different type of operators and state functions. Now we can discuss the how to find the eigenvalues and eigenvectors of an operator. That is, we can discuss the eigenvalue problems. So let's start eigenvalues and eigenvectors of an operator. A state vector ket psi is said to be an eigenvector or eigenstate of an operator A if on the application of A over ket psi gives A ket psi where A is a complex number called the eigenvalues of operator A, and this equation is known as the eigenvalue problem or eigenvalue equation of the operator A. Its solution yields the eigenvalues and eigenvectors of operator A. A simple example of eigenvalue problem for the unity operator is unity operator operates on any ket psi gives unchanged ket psi. This means that all vectors are eigenvectors of identity operator with an eigenvalue 1. Now let us suppose an operator applied on a ket psi gives a eigenvalue a and ket psi state vector. Then this implies that if we have operator to the power n applied on ket psi, then it gives the eigenvalue a to the power n with ket psi. And if the operator is function operator, then in that case, if it is applied on the ket vector psi, then it will give the eigenvalue function f with ket psi. For example, if operator a is e to the power I a, then when it is applied on ket psi, then it will be greater than e to the power I a ket psi. So friend, we see that the eigenvalue equation or any function operator gives the eigenvalue function with eigenvector psi. Now the eigenvalue problem operator A ket psi is equal to eigenvalue A ket psi. Now we will work out the metric representation of this eigenvalue problem and solve it. That is, we want to find the eigenvalues A and eigenvector psi of an operator A such that A ket psi is equal to A ket psi, where A is a complex number. And to solve this, let us insert a unit operator between operator A and eigenstate ket psi, and further multiplying by bra phi m. Therefore, we will have bra phi m operator A unit operator summation n pi n pi n ket psi is equal to pi m a ket psi. So we have summation n a mn pi n ket psi is equal to a phi m psi is equal to a summation n bra phi n ket psi delta n m, which can be rewritten as summation n a m n minus a delta n m bra phi n ket psi is equal to 0. So we have this equation to solve for getting the values of eigenvalue and state vector, where a m n is equal to bra phi m a operator a phi n, and this equation represents an infinite homogeneous system of equations for the coefficients phi n psi. Since the basis ket phi n is made of an infinite number of base kets, this system of equations can have non-zero solutions only if its determinant vanishes. So to give the non-zero solution, this value should be 0. Therefore, therefore determinant a n m minus a delta nm is equal to 0. Now for the simplicity, we take only nth terms. We take only n terms so that to converge this equation. So determinant a1 1 minus a1 2, a1 3, and so on, a1 n, a2 1, a2 2 minus a2 3, a2 n, and so on, an 1, an 2, an 3, an n minus a is equal to 0. This is known as the characteristic equation or the secular equation. The solution of this equation yield the n eigenvalues a1, a2, a3, dash dash an, since it is an nth order equation in A. The set of these n eigenvalues is called the spectrum of operator A. Knowing the set of eigenvalues a1, a2, a3, dash dash an, we can easily determine the corresponding set of eigenvectors phi1, phi2, phi3, dash dash phi n. For each eigenvalue am of operator A, we can obtain from the characteristic equation the n components of the corresponding eigenvectors ket phi m. So n components are phi 1, ket psi, phi 2, ket psi, and so on, phi n, ket psi, n components corresponding to the eigenvector phi m. If a number of different eigenvectors have the same eigenvalue, this eigenvalue is said to be degenerate. Same eigenvalue is related to more than two eigenvectors, then this eigenvalue is said to be degenerate, and the order of degeneracy is determined by the number of linearly independent eigenvectors that have the same eigenvalues. So friends, this is for now. We wrap up the lecture. Hope you enjoyed this video lecture and learnt about the eigenvalue problem and how to solve the characteristic equation to get the eigenvalues and corresponding eigenvectors. Friends, if you like this video, please press the like button and share with your friends so that they can also learn about these concepts. And if you are watching for the first time, please subscribe the Sai Academy channel so that you can get the notification of the upcoming videos. Thank you, friends.